The kidney is an important organ for controlling the small molecules that are circulating in the bloodstream, the nutrients and toxins. The nutrients, of course, we would like to retain in our bloodstream, and the toxins we'd like to get rid of. So now we're going to consider how reabsorption and secretion provide mechanisms for this. And I've mentioned this functionality previously. So as we focused on the urinary system, we've talked about how the blood is filtered. In the last lecture, we focused on how the concentration of dissolved particles is controlled in order to effectively adjust the osmolarity of the blood or maintain that osmolarity by producing urine over a range of osmolarities. Now we're going to talk about these processes of reabsorbing nutrients from the filtrate, that is the small particles that we want to retain in the body, and the process of secretion, where we deposit toxins into the filtrate so that they become a part of the urine. And so the question here is, how does the kidney retain nutrients? And a secondary question would be, how does it get rid of toxins? So reabsorption is the process of retaining the nutrients. And this is studied classically in dogs with a really simple experiment. You essentially feed dogs sugar water and you measure how much glucose is in their urine. And so what we have on the x-axis of this plot is the concentration of glucose. This can be manipulated by giving dogs sugar water of varying concentration, and that glucose gets absorbed and that's reflected in the bloodstream. On the y-axis, we have the rate of production. That's how many milligrams, in this case of glucose, are produced in the urine on average per minute. And what might be a little surprising is that at first, at low concentrations, you don't see any glucose in the urine. So maybe that's not surprising, because after all, glucose is a really essential nutrient that all of the cells of the body use to produce ATP. So that's good stuff that we don't want to be urinating out. Now, what is happening at this low range of concentrations? Well, glucose is small enough that it is filtered through the glomerulus and gathered by the Bowman's capsules in the nephrons within the kidney. So as a consequence, if it's not going to make its way to the urine, that must mean that it is being reabsorbed. And so for this range of concentrations, we can infer that reabsorption is equal to filtration. If we drive the glucose concentration to higher levels, however, then what we find is that glucose starts appearing in the urine. And it appears more and more as we increase that concentration. And one hypothesis for what happens here is that the reabsorption is being driven by a pump. We now know that reabsorption occurs through essentially the same mechanism as I detailed in an earlier lecture for the absorption of glucose from the gut lumen and the small intestines into the bloodstream. In this case, it's going from the lumen of the tubules of the nephron and being deposited into the bloodstream. But it's the same basic process. You've got sodium potassium ATPase doing its primary active transport, a secondary secondary active transport achieved by a co-transporter, and then facilitated diffusion through the basal membrane so that it makes its way into the interstitial fluid and then ultimately the bloodstream. All right, the point is that there's a pump, and there's a region of the membrane within the nephron that has those transporters, and there's a fixed number of them. So it can only handle this pump altogether. Imagine all the cells with all those transporters. We can call that a pump. That pump has a maximum. It can only handle so many molecules of glucose per unit time. So if you saturate the pump and then drive it even further, the glucose is going to pass by the pump and make its way into the filtrate that becomes the urine. So what's happening on the positive slope of this curve is that reabsorption is occurring at a lower rate than filtration. And what's left over is what appears in the urine, okay, this excretion rate. So excretion, if you'll remember, is the term we use for what is actually deposited into the urine. It's what is urinated out. So this is a characteristic curve not just for glucose, but for other nutrients that are reabsorbed in the nephron. So for glucose, phosphate, calcium, and magnesium under the normal range, you have a rate that is filtered, okay, at a rate of 100 milliliters per minute. And in a region called the proximal tubule, which we haven't talked about yet, are the pumps for reabsorption. Okay, so we did talk about the distal tubule. That's over here. That's the part of the nephron right before the collecting duct. This is the proximal tubule, and a lot of reabsorption occurs in that region. Now, if 100% is reabsorbed, then we would expect none to make it into the urine. So there's a zero clearance rate, is the term that we use. What is clearance rate? Well, clearance rate you can think of as being the slope of the curve on the right. So beyond that normal range or the low concentrations where we start to have a positive slope, we could measure that. And it's just the slope. So it's the change in the excretion rate as a function of the change in the blood plasma, in this case for glucose. But it'd be the same basically for phosphate, calcium, magnesium. Now what we can do from this very simple measurement, and by the way, even though this is a classic experiment, this is repeated all the time in diagnostics on kidney function. So people are asked to pee into a cup, and then concentrations are measured of substances in the urine. And then inferences are made about what the kidneys are doing successfully or unsuccessfully. So one inference that can be drawn from the clearance rate is how much of that substance is being filtered. So even at low concentrations, filtration should occur. It's a passive process. So we can infer from that positive slope the glomerular filtration rate. Okay, so that's the filtration that happens in the glomerulus. The reason at low concentrations that we, of course, don't see that in the clearance rate is because it's being reabsorbed. And so we are also going to infer the reabsorption rate as the red curve. We know that these substances are actively pumped back into the blood. Those pumps reach a certain saturation point at a certain concentration. And beyond that, the reabsorption rate is maxed out. It's fixed at that constant level. So at saturation, then it maintains at higher concentrations that rate. That allows, because that is fixed, it allows the remaining glucose to pass through, which is what is cleared. That's the excretion rate. What about other substances? So not everything is reabsorbed at 100%. We saw an example of urea when we were talking on a previous lecture about how urea plays a role in the osmolarity gradient in the interstitial fluid around the nephron. So in that case, urea is reabsorbed at a 50% level. And so the urea that gives urine its wonderful smell that emerges in the urine is the other 50%. So 50% is excreted, 50% is reabsorbed. There are also substances that are actively secreted by the urinary system. So let's take a look at how that works. We have, for those substances, and these are toxins that are produced by natural processes so that your essentially your kidneys can recognize them as waste products, as opposed to maybe drugs or things, synthetic substances that might not be natural products that can just be filtered in the glomerulus. And actually one feature of the sort of design of the kidneys, if you will, is that they tend to get rid of anything that's small. And nutrients like glucose that are dumped into the filtrate are actively reabsorbed because your body recognizes that as something good. And what I'm going to describe now is a waste product that your body can recognize. The things that aren't recognized will be filtered. And that's a way of getting rid of it from your bloodstream. So one of these sort of natural toxins is creatinine, which is produced as a byproduct of protein metabolism. And what we see here is that there's no reabsorption. It's filtered in a similar way as glucose. So we have the same rate of filtration occurring there. There's no reabsorption in the proximal tubule, but instead we see that there's active secretion, that is binding creatinine from the bloodstream and depositing it into the lumen of the tubule so that it becomes part of the filtrate. So we see that occur in the proximal tubule, the loop of Henle, and in the distal tubule, so that you get a clearance rate here that is greater than the filtration rate. So the way that looks in the experiment on the right, and creatinine, by the way, is a diagnostic for kidney function. So it is common these days to make measurements of creatinine from urine. So what does it look like? Well, the secretion process is similar to reabsorption in that it's effectively a membrane pump, but it's obviously operating in the opposite direction. But it has a similar curve as the reabsorption curve that we considered for glucose. In this case, secretion increases as a function of creatinine concentration in the plasma. As more creatinine is available, then more is secreted. And it will saturate so that at higher concentrations, you're stuck with that fixed secretion rate. Now, bear in mind the simple math of things that are excreted. The excretion is equal to the filtration of a substance minus the reabsorption, moving it back into the bloodstream, plus the secretion, the things that are actively added to the filtrate. So in addition to filtration, the filtration curve, we can add the secretion curve, which gives us an excretion rate that looks different from the curve that we had for glucose and magnesium and other good stuff. So in this case, we see that we're adding those two curves, and as a consequence, we have a very positive slope in this relationship, the clearance rate, at low concentrations, and then a less positive slope at the higher concentrations. So what creatinine demonstrates is what you have in the case of an active secretion of a substance that is also filtered and there is no reabsorption. And glucose and the curves for glucose illustrate where we have reabsorption and filtration, but no secretion in the excretion of that substance as well.